to sum this part up, let's look at the basic rules that control how elements react, the activity series. Now, Killerby states that this will help us understand why some elements replace others, how metals react with acids in different ways, and why certain metals release hydrogen even when in contact with water. This also connects back to our graphs of spontaneity and the strength of reactions in oxidation and reduction. All right, so let's focus on this list, or again, the activities series. Now, metals are arranged based on their capacity to replace each other in water solutions. Of course, this is going to affect how they react with acids and water itself. So in a chemical reaction, a metal can reduce another substance when the overall cell potential or standard cell potential is positive. Now, let's apply this mini understanding by exploring 4 different displacement scenarios using this overall series. The first scenario is when a metal can actually displace H2 from acid. Another way of saying this is that a metal can reduce H+ to form H2 gas. Next, we have scenarios where metals are unable to displace H2 from an acid. And then we're going to talk about metals which actually can reduce water, right? Or another way of saying it is that it can displace H2 from water, okay? And the fourth is going to be where metals can displace other metals. So let's go ahead and get into it. So how do we kind of get this started? Well, first, we're focused on our She cell or our H2 here. That is going to be where our cell potential or our reference cell potential is 0.00 volts. All right, folks? Now, metals that actually can displace H2 from acid are going to be metals that are stronger reducing agents than H2. So anything above it in this chart, you're going to see stronger reducing agents. Now, sometimes you can have different activity series. Like if you go Google something that you want to get like another view of this, you will see that it could be reversed. All right, folks? So you'll see like H2 here, and then below it, we'll have all the metals that you see here, and then above it, we'll have these metals here. You can sometimes see it that reverse way as well. But either way, the understanding is going to be the same. So what do we need to do? First, you choose a metal from the list, and then you're going to write the half reaction of that metal. And since we're using our She cell or our standard electrode, right, then that means that if this automatically is going to be our reduction, that we're going to use it here for this example, and of course for all of our examples, and then anything above it has to be oxidation. So when you write your half reaction, you're going to write the half reaction as oxidation. Therefore, you can take that half reaction as oxidation, combine it with the She half reaction, and then when you combine those, if your E0 of the cell overall is going to be positive, then you actually have the ability to reduce H+ to form H2 gas. But if E0 of the cell is going to be negative, then of course you cannot displace H+ to form H2 gas. Another way of saying that is you can't reduce the H+. Let's get into our first overall example, which is going to be the scenario where we actually do have metals having the ability to displace H2. So that means we're looking for an E0 of the cell that's going to be positive. So first we pick a metal. We're going to be choosing iron. We have our half cell reaction for iron. Of course, we need to make sure that we write it in reverse because it's going to be focused on oxidation here. So I'm going to write it in reverse. I have my iron solid. It's going to form Fe2+ and 2 electrons. It has a standard half cell potential of negative 0.44 volts. Again, this is oxidation, it's at the anode, and our She cell is at the cathode, and it's going to be reduction. When we combine both of these reactions, we get an overall, and then of course we can go ahead and calculate our E0 of the cell, which is going to be 0.00 volts minus a negative 0.44 volts. So we actually get a positive overall cell potential. Because we get a positive overall cell potential, we definitely can say that this iron definitely can, again, displace H+ to form H2 gas. Now, even though iron, being oxidation, had a lower standard half cell potential here, it still had the ability to displace H2 because the overall cell potential was positive. We can then start gathering more patterns just from this understanding. Like, I don't know, the more negative the standard half cell potential of a metal, the more positive the overall standard cell potential will be, for example. Right, folks? Or you can end up saying the more negative standard half cell potential of the metal, the more positive standard half cell potential of H+, okay? Or the reduction of H+. And therefore, the more active a metal is. So as we can see from our chart, metals that are going to be above H2 can reduce H+ from acids, and then metals that are below it cannot. Okay, folks, so let's go ahead and get into the example of metals that are unable or cannot displace H2 from acids. So here again, we're going to get our half reaction. It has to be in oxidation. So I'm choosing silver here, and it has a standard half cell potential of 0.08 volts. Of course, the C shell is still going to be 0.00 volts. When I get my overall E of the cell, I get a negative number. So negative 0.80 volts. Therefore, this silver cannot displace H2 from acid. And usually metals are going to be below the H2 here in this overall activity series are going to be weaker reducing agents, as we can see from this arrow, because as you go up, you increase the strength of reducing agent. So if we're down here in this portion, they definitely are going to be very weak reducing agents. You also can say that these metals are going to be less active. All right, let's go into the third scenario of displacement, which is going to be metals that can displace H2 from water, not acid, from a water. So that means we're no longer using the sheet cell here. We are going to be using the overall half cell for a water molecule that's going to be forming H2 gas and 2OH minus. It kind of falls along like in between the zinc and the sodium here. We actually see this overall reaction in the activity series. It has its own, of course, standard half cell potential, which is negative 0.83 volts. So that's what we're going to be using as our kind of anchor or our reduction here. Therefore, we're still going to write the same half reaction. Of course, it's still going to be oxidation, and we're still going to see what the overall E naught of the cell is going to be. If it's positive, it still has the ability to displace. If it's negative, it doesn't have the ability to displace. The only difference here is we're using a different half cell as our reference. All right, so I'm just choosing sodium here. Of course, I have to write sodium in oxidation, and so I'm just choosing sodium, which is right here. And that's an oxidation. It has a standard half cell potential of negative 2.71 volts. Of course, what we're comparing it to is going to be our cathode or reduction, our other half cell, which is based on the negative 0.83 volts we saw above. When we put these two together, we get a positive E naught of the cell, meaning that this sodium has the ability to displace water and form H2 gas. Another way of saying it is that the sodium was able to reduce water to form the H2 gas, and of course the 2OH minus as well. And of course, because sodium is a group 1 metal, we kind of are seeing the group 1 metals will have the same kind of effect. And also we can see a group 2 metal like calcium, which also can displace or reduce water to H2 gas. Okay, folks, so this is an example of that. Same half reaction as oxidation, same reduction reaction for water, and then same overall cell reaction to show that that's actually going on. And then finally, we can also predict whether one metal can displace another from solution. How do we do that? Well, now we can look at our list, right? So let's have an example of zinc and iron. So here's our zinc here, and here's our iron here. As you can see, zinc is going to be higher up on the list. If it's higher up on the list, that means that zinc definitely wants to give up its electrons way more than iron would. We're not saying that iron doesn't, we're just saying that zinc will do it more. So zinc automatically is going to be oxidation, and then anything below it will be reduction. All right, folks? So what do? We go ahead and write our half reactions, and then we go ahead and get our overall standard cell potential. And if it's positive, like we said, it will displace. And if it's negative, it will not displace it. All right, so I have my zinc half reaction. I'm going to reverse it to show its oxidation. And then, of course, I have my iron, which we know is going to be lower in the list, so definitely going to be our reduction. Now, when I combine these, I get my overall reaction, and I can go ahead and calculate my E naught of the cell, or my standard cell potential. That's going to be negative 0.44 volt minus a negative 0.76 volt. This is equal to positive 0.32 volts. So if I ask the question, can zinc displace iron? The answer is yes, because the standard cell potential is positive. And of course, we can verify this by the numbers given. The zinc is more negative. So if it's more negative, we automatically know it's going to be oxidation. And we also know that if it's more negative, it tends to give a more positive standard cell potential. And then, of course, when we have a less negative one, automatically that will be reduction, just like we saw. All right, folks, well, Killer B says we out, yo. The second part of the Volchitsil Jitsu is complete. Now on to our last villager to explain the last part of the Volchitsil Jitsu, which is how cell potential or voltage relates to free energy and equilibrium constant. And of course, its associated calculations. See you there, folks.